In this talk, we provide counterexamples to the invariant circle packing problem. The circle packing is a collection of disjoint circles in the plane. Here you can see two circle packings of the whole plane and a unit circle. A unit circle is regarded as the hyperbolic plane. The tangency structure of the circles defines a planar graph. There is a famous theorem of He and Fromm that says that under some assumptions on the graph, every planar graph has either a circle packing in the whole plane or in the hyperbolic plane. And if the circle packing, if the graph is a triangulation, then there is a uniqueness result, which says that in the Euclidean case, the CP is unique up to isometries and scaling, and in the hyperbolic case, the CP is unique up to isometries of the hyperbolic plane. In recent years, there has been some interest in circle packing of unimodular graph. A unimodular graph is a random rooted graph that is heuristically, statistically homogeneous. The counterpart in the context of point process theory is stationarity. We can define a stationary CP as a random CP such that its distribution is invariant under all isometries. These two notions have a lot of connections. In particular, for circle packings, if you have a stationary CP, then the graph that it defines is a unimodular graph. The other side is a problem studied by Benjamini and Timar. They prove that in the hyperbolic case, there indeed exists stationary circle packing in the hyperbolic plane. But for the Euclidean case, they pose it as a problem. Here we show that the answer to this problem is negative, which means that there is a circle, there is a unimodular graph that has no stationary circle packing in the Euclidean plane. Let's review the proof for the hyperbolic case. The first point is that since the CP is unique up to isometries, the radii are uniquely determined. You can still apply an isometry, do this such that the circle of the root is centered at the origin, and then apply a random rotation around the origin. Here you obtain a CP that satisfies the mass transport principle, so it is the Palm version of a stationary point process. In the next step, you can convert it into a stationary circle packing. What's the problem in the Euclidean case? The problem is that the first problem is that radii are not uniquely determined because you can scale the circles. But for some graphs, one may still choose the radii without looking at the root. This is enough to go to the third step to have the mass transport principle. At this stage, we call the CP point stationary, or a unimodular CP defined by Benjamini and Timar. The next problem is that to convert it into a stationary CP, one is that a certain set has finite expected area, which might fail. So we strengthen our result to show that our example has no point stationary CP. I want to justify that the second result is more interesting. The proof of the first result is very easy, but the second result gives more information about the graph. As I said, if there is no point stationary CP, then one cannot choose the radii without looking at the root. One way to do this would be to consider a global quantity like a spatial average of the radii and scale it such that the spatial average is 1. So this implies that in our example, there is no way to define a spatial average. And there are a large number of very large circles and a large number of very small circles that makes it impossible to define a spatial average. So here is the example. Let's start with graph Z and fill the upper half plane with a triangulation. Choose, for example, connect the vertices alternatively, choose between the two options randomly, and then go to the next layer and choose between the two options randomly, and so on. This defines a triangulation of the upper half plane. This graph is unimodular since it is stationary under horizontal shifts. And reflect it, connect each vertex to its reflected image, and fill the squares with triangles as follows, as shown. This graph has the property that it has a unique automorphism other than the identity. So its CP has a unique symmetry line. This easily implies that there is no stationary CP, because if so, the symmetry line would be a stationary random line, which is impossible. The point stationarity is more difficult. First, note that each point is adjacent to its reflected image, so the corresponding circles should be both tangent and symmetric. So it is enough to show that the upper half of the graph has no point stationary CP, such that all cycles have a common tangent line. The tool to prove this is to approximate the graph by finite graphs. Assume that we have a sequence of finite unimodular graphs that converge to our unimodular graph. And we have a circle packing of the finite graph that after scaling converges to some circle packing of G. For example, you can scale it such that the radius of the root is 1. And our result is that if this condition holds, then you can scale P to obtain a point stationary circle packing. This is for existence. We need the reverse of this. Note that here, this is the ratio of two quantiles of the radii in the circle packing. And the condition says that this ratio should not go to infinity as n goes to infinity. It should satisfy this problem. We need, here's the proof idea. Since the root is uniform among the vertices, so the distribution of the radius of the root is just the empirical distribution of the radii. The idea is to scale Pn such that a global quantity, such the median radii, is 1. And to use the assumption to prove that the scaled circle packing still converges. We need a reverse of this, and we can prove the reverse under the stronger assumption that Gn is a subgraph of G. We want to apply this to our graph. Note that the triangles have a tree structure. Each triangle has two children and one parent. Since the triangles are in bijection with vertices, this defines the tree structure of the vertices as well. Here's a portion of the graph, the tree structure. First condition on the event that the root is in the last layer, and define Gn as shown in the picture, go in step upwards and consider all of the points below that point. Actually, this is not the graph that we want to use the theorem. We consider only the last layer and its intersection with Gn. Note that there is no H here, but this is not a problem since we already have a circle packing of H, and we want to show that there is no way to scale it to obtain a point stationary CP. So we still can use the theorem. Here is part of the graph H2 shown. These four circles here, and the four lowest circles are H2, and here is the graph G2 shown. Note that the whole construction is determined by the two top circles because the radii satisfy this equation. So if to each triangle we assign two quantities, then the children are defined by multiplying by two matrices. So we will use central limit theorem for products of random matrices to show that the empirical distribution of the radii in Hn is approximately log normal with large variance. This implies that the ratio of two quantiles converges to infinity, and so there is no point stationary CP. Here is the second example. Modify this the previous example such that each triangle has either 0 or 2 children independently. In our previous work, we have shown that this determines a unique unimodular family tree. Note that the family trees are directed here. And here is the construction. Start from a root triangle and choose one of the two possible parents randomly. And for that, choose one of the two possible parents randomly and continue so on. You define the ancestral line. And for each of the ancestors, choose the other child as well. We have decided for the ancestral line. For the other vertices, choose either 0 or 2 children, as shown here, and continue indefinitely. This defines a triangulation of the upper half plane. We remark that this is the limit of a random triangulation of the n-gon. And then, as before, reflect it and connect each vertex to its image and fill the squares to obtain a unimodular triangulation. The point of this structure is that there are infinitely many layers both above the root and below the root, and each layer is infinite, and more importantly, the layers are indistinguishable, which can be defined by some ergodicity. Note that in each of the triangles, the middle vertex has a smaller circle. This implies that the radius of every point is less than the radius of its parent. So heuristically, every layer has smaller circles compared to the upper layer. This should be made precise since there are infinitely many layers We will quantify this and prove this inequality, and this contradicts that the levels are indistinguishable. To prove this, note that each point has a next point on the right, and if there exists a point, a stationary CP, then the CP is stationary under moving to the next point on the right. This enables us to use Birkhoff's ergodic theorem to define the average radii in each layer, or a function of the radii to make it bounded. And the next step is to prove that we have indeed this inequality. The problem is that in each layer there are some vertices without children, so the radii, their radii might affect the average and make it difficult to compare two layers. This can be done. This can be done by noting that conditioned on the upper half of the graph, the points in the lowest layer have either 0 or 2 children in an IID manner. So using this IID, we can indeed prove this inequality, and this distinguishes between the layers, which is impossible. And here are the references to my work and the work of Benjamin and Timar. Thanks for watching.